So thank for invitation. So the topic for my talk actually is on COVID-19. So the title is Integrating AI in Imaging, Quantification, and Adaptation of COVID-19. Actually, we have done a lot of work, and I just show you some of the work in this slides. And with the long infection quantification and also large scale screening for COVID-19. And also we developed method for severity assessment. And also we are invited to write a review paper for IEEE journal. The title mainly like review artificial intelligence for image data acquisition, segmentation, and diagnosis. And recently, we also have the paper accepted by IEEE session on the medical imaging. It's mainly for diagnosis of COVID-19 from community-acquired pneumonia. Besides the work we have done, and I also did a lot of organization work for COVID-19, particularly 3 special issues. One actually is a special issue on IEEE session on medical imaging, and this I think is the first special issue on the engineering journal for COVID-19. And also I co-organized with the teaming and other colleagues for the medical image analysis. And this is the third one on the pattern recognition journal. Actually, this will be announcing very soon. So this is my work for organizing special issue on COVID-19. And also, as you know, we are organizing MICCAI webinar for imaging AI-based management of COVID-19. And we already have 15 speakers, and the talk will be on May 14 and May 15. So in this talk, actually, I will basically talk about how the AI can be applied in the whole pipeline for the imaging, including contactless imaging, infection quantification, and also severity assessment. I will talk one by one. So first, I will talk about contactless imaging. The goal is to try to protect technicians from infection during the imaging. For example, this is a conventional imaging workflow. Technician has to be with the patient to post the patient on the table of the scanner. And also, technician has to adjust the relative positions between the patient and the X-ray tube. So in this way, technician has more chance to be affected by patient. And so the goal for the contactless imaging is we want to do automated patient positioning. This is a picture from United Imaging. And basically there's 2 rooms. One room for patient in the scanner. So basically patient will go inside the room. And in these rooms, there's a camera over there and the technicians actually in another room. Technician can see everything through the camera. Of course, most important is this camera is an AI-based camera that can automatically measure any body parts for the patient, then adjust the tables. So this is the picture, as you can see, for example, patient lie down on the table, and the technician can see from the screen. The next movie, also from United Imaging, you will see, for example, patient moving inside automatically. And I will tell you how to do that, use the AI to identify basically the lung lesions. You see the lung lesions, automatically scan the lung. In this way, technicians will not need to be with the patient. In this way, you can protect the technician from infection. So we go to the detailed step. How can we do the automatic patient positioning? For example, firstly, using the camera on the top, you will have the patient image like this. Then you identify all the major points on the 2D images. Then you will using AI-based technique to recover 3D meshes on the top of these 2D images. Then if you want to scan the chest area, it automatically localizes starting points and ending points, then move the tables. In this way, the scanner can automatically scan the patients. So this is just pictures taken from the application area. For example, this is images acquired by the video, and you can get, if you want to scan, so this is a head area, and this head area automatically mapping to the template in the computer. If you want to scan chest area, it can automatically also map into the chest area, then with the confirmations by the technician, then the scanner can scan the patient. Here I will show you, in next 2 slides, I will show you some pictures how robust this technique is. Firstly, this is images we can automatically identify lead points as the key points for the 2D image. You can get mesh, and also basically this is a side view. You also can get mesh robustly, and the back view, even back view, you can also generate the meshes on the top of this 2D image. And this is just, you can see this is the reverse directions for the patient, and you still can identify key points and recover 3D mesh robustly. In the scanning room, it's usually dark. Even in the dark environment, this technique can also work very well. And also in the COVID-19, people may wear masks. It's also doesn't matter for this technique. And people can lie down in the different poses. Even, you can use your iPhone or, Huawei phone to block your face. Algorithm can still identify the key points and then can generate the mesh. So this technique actually not only apply in the CT, you can apply also in the DR or for X-ray. For example, this device line now actually is even taller than the subject, but with estimated all the body parts by the camera automatically, you can move this device just align with the chest area, then scan the images. And also, subject can lie down in any pose. This algorithm can work. And these 3 images basically show you algorithm is also very robust to the lighting. For example, you can put lighting on the arm, then the meshes can still generate very well for the whole body. You just pay attention to the pink arrow. So any area you want to scan, AI technique can automatically localize it. Actually, this is a technique already have the live demo in ISNA last year. ISNA, most of people you may don't know, ISNA stands for North Radiology Society in North America. And this is the area, it's a very popular area. All the people, when people visit to see imaging device from United Imaging, and all the people will try to stand there, and how the technique basically can robustly estimate mesh for each of subject. As you can see, for example, the yellow one for the body, and also the green one for the hand, and also the leg. One leg is pink, and the leg is white. So it's very, very robust. But this kind of technique, as I mentioned, can be installed not only for the CT and also DR. Also, you can apply with MI and also molecular imaging, even radiation therapy device. You can use it to for the patient positioning and also motion monitoring. This technique also can be applied to the mobile CT platform. In the COVID-19, actually CT is used a lot in China, and we know CT is installed in the basement or first floor in the building. But when you need a CT urgently, and you don't have any room in the building to install the CT, so this mobile CT platform perfectly matching for this requirement. And this mobile CT I called is like all-in-one, means for example, even you have the air conditioning, and this platform actually separated into two rooms, as I mentioned before. One is for the scanner, another is for the technicians. And the patients actually go through this room, this door, and go inside the scanning room. And another door is here for the technician. Technician go into his own room. Then the camera on the top, we call the AI camera, as I mentioned before, can automatically estimate the 3D measure for the patient, then move the table, adjust the table, and then with the confirmations by the technician, and the scanner can automatically scan the subject in this way. So basically, like I mentioned in the early, we can protect the technicians. As we know, in the COVID-19 in China, although in the other country at this time, actually technicians and medical doctors, they are infected a lot. So this technique can protect our technician. In the future, we hope we develop a lot of AI technique to also protect our physicians. They are the people helping us. So after talking about countless images, I'm going to talk about how the AI can be applied for quantify infections for the images scan. Think about when patients still in the table of the scanner and you acquire the images. At that time, we needed to segment infections in this way. You can automatically quantify the infection and evaluate even the severity of the COVID-19. So these are the slides that basically show you, for example, for the COVID-19, this is a radiomic patterns. You have the GGO standard for the ground glass opacity, and also other pattern. I will show you a lot of this kind of CT images in the later slides. And also remember GGO. GGO actually is one of the very important imaging biomarker for the COVID-19. So as I mentioned before, we were invited to write a review paper for IEEE review in biomedical imaging. I believe this journal will have very high impact very soon, because all the paper are the review paper, and the review paper usually have more citations than regular paper. So in this review papers, actually we summarize all the AI-based segmentation algorithms. These are some example. In summary, actually, 67% of the papers are using UNet, and 22% of papers use UNet plus 11 papers use VBNet. And this method is used for the long segmentation, long and lobar segmentation, and also the region segmentations. So this is just one slide show you how to do the segmentation. Actually, in our segmentations, we use a VBNet and we try to segment infections. This is 3D rendering for the segment infections. And we also want to segment simultaneously for the 5 lobar and also 18 segments in left and right lung. Actually, there's a lot of innovations you can do for this framework. Even, looks like a VBNet is very easy, but you still can do a lot of innovations for application of the COVID-19. For example, when you design the loss functions, we usually define loss function for each of the lobar. For example, this is a neighboring lobar. We design the loss function like, for example, dice ratio for this lobar, for the bottom lobar, but there's no any crossing errors you can measure for them. In this way, actually, bottom lobar can be segmented in the top of the middle lobe because you don't have any constraints on them. Then actually you can define cross errors between any neighboring lobes or neighboring segments. In this way, you can make the algorithm very, very robust. And although there's other innovations in this development, and what we called, or many of you know, a technique called human in loop. Means, algorithm and human, particularly radiologists, will work together. remember, in the beginning of this COVID-19, you don't have a lot of basically images, manual labels with infection or manually segment for the lobe and the segments. But time is very, very important. Like United Image Intelligence, they have to develop this kind of technique within 5 days. 5 days. Remember, that's just 5 days. So, but initially you don't have a lot of this kind of training samples. And in this way, we use a technique, as I mentioned, the human in loop. Means, you use a small number of the manual label sample to train the initial VBNet. Then you apply this VBNet on the remaining samples without manual segmentations. Then you select some of them for manual collection, and then include them in the training set to train the second VBNet. You can do this one by one. And there's one important question here. People may not pay attention. For example, I mentioned you can select a new sample after automatically labeled by the VBNet you trained before. If you select samples with a very good segmentation result, that means these samples is very similar to the training samples. In this way, you can only enlarge in the training domain slightly. In another case, if you select samples with a very bad segmentation result automatically, means these samples are very different from the existing training samples. If you can do manual collection for them, you can quickly enlarge the training domain. Then, if you include those samples, the next VBNet trained can pick a larger domain for the training sample, and your performance can be a geometric increase. Of course, in the later case, you have to spend more time, manual times. In the first case, relatively small amount of time. Of course, in this case, you can use like in-between algorithm. For example, some samples you select with a very good automatic segmentation result. Some samples with very bad segmentation results. In this way, you can increase your training domain in the neighboring area and also beyond the neighboring area. So in this way, the algorithm can be training better. So I just spend some time how we use a human in loop to make this segmentation algorithm powerful and powerful. So then when we develop these algorithms, and we also have all the software packages installed in the hospital, I will mention later. And then this software package can automatically check each of the subjects you just scan. For example, in the next slide, I will show you for the more details, we can firstly segment the infections. And also, as I mentioned before, we will segment lung. Lung, you have the left lung, right lung. And then we will know how much infection in each lung. We can also segment the lobe. For example, for the left, we have 2 lobes, and the right, we have the 3 lobes. And we know how much infections in each of these 5 lobes. We can also segment the lung into 18 segments. Then we know infections in each segment. Most importantly, for each segment, each lobe, or each lung, we can also do the component analysis for the infections. As you can see, we separate into 1, 2, 3, 4 different segments. And for GGO, actually this is origin area is HU value for GGO. For example, from negative 750 to negative 300. This values basically depends on the physician may changing, but this is the area for GGO. And then very interesting and very important for this technique. Just in China, in the initial stages, patients, particularly for the severe patients, they will scan every 3 to 5 days. They will have the CT images. in this case, you want to compare. For example, this is image taken at the current time, and this is the images acquired previously. For example, 3 or 4 days ago, 3 or 5 days ago. Then you can, of course, automatically segment infections. And more importantly, you can compare the component for the infections you segment for the previous time point and the current time point. This is a histogram for the HU in the previous time point, and this is a histogram for the current time point. And you see this histogram of HU values move to the left side. The left side is the healthy side for the lung. That means, for these patients, after 3 or 5 days, patient is recovering from the COVID-19. So this, you can do the quantitative comparison for the different time points. This is the beauty of the technique. It can do automatically. Of course, this kind of technique can be applied to all the longitudinal images from the same subject. For example, this subject scanned on January 21st, 24 and 27, then the February 7 and the February 6. You see this color. This is the infections, more infections on February 2, and this is February. This is, for example, infections reduced, basically absorbed due to the treatment on February 7. So you can see this kind of changing. And in the later slides, I will show you more this kind of longitudinal CT images for the patient. And this technique has been included in this kind of workstation and has been installed about 100 hospitals in many regions in the China and other foreign countries. Some of you, in China, you may know some companies, they advertise for install their system in foreign countries, but United Imaging Intelligence did not have any kind of advancement on this, but we do have, installations for several countries. And we have this kind of software packages in more than 20 hospitals in Wuhan, including the 5 God Mountain Hospital. As you know, this is one of the 2 hospitals built in 10 days. This is very fast speed in China. And also this system is installed in the top hospital, including Beijing Hospital and also West China Hospital of Sichuan University and the Peking University People's Hospital. Besides install this workstation-based system, we also installed in the cloud. Then the remote hospital can access through the cloud, use our system. So I just finished talking about continuous imaging and automatic method to segment lung and other infections. Next, I will talk more about our technique, how we can basically assess the severity. I'm going to talk about 5 different methods, 3 methods actually based on the multiple view learning, sparse learning, and 2 methods based on the deep learning algorithm. So the goal here is to do the identification for the infection, also severity assessment, and also predictions. Here, I will show you how this AI techniques can be applied for example, when you acquire the image, just like I just mentioned for the first part of my talk, continuous imaging for the scanner, CT scanner, then you acquire the CT images. Next questions immediately you want to ask before you send these CTs to the radiologist. Algorithm, AI-based algorithm can do whether this subject has COVID-19 or just is a community-acquired pneumonia. So for the different case, you will treat them differently. So this is like identification from the COVID-19 from the CAP. CAP stands for the community-acquired pneumonia. I will use CAP in my later part of the talk. Then if your algorithm automatically, after scan the images, automatically estimate this, and you found this is a COVID-19 subject, and you will inform technicians, and you have to do the special case for this subject. Of course, when you try to treat this subject, or you want to send this subject to which kind of hospital, the hospital deal with a severe patient, or subject deal with a mild, COVID-19. So this is another AI technique based on the identified COVID-19. You will estimate where this subject is mild or severe for the COVID-19. And then after you finish it, asking these two questions, of course, you will have two AI algorithm I will talk about later. Then the third questions you are going to ask is basically, if this subject has a mild COVID-19, and you want to ask, this is also very important, questions physicians will ask, where this mild COVID-19 subject will progress into severe or not. If this subject is going progress to severe, then you have to very special treatment for the subject. Otherwise, you will use a regular treatment for this subject. So all these three questions, I will firstly introduce three traditional or conventional machine learning algorithm to achieve this goal. So I will focus on this one first. And of course, as we summarize in our review papers, we also, summarize, all this kind of diagnosis prediction method. And some method, for example, 60% of papers using CT, and 40% of the papers using X-rays for this, all the tasks they want to answer. And also, 50% of the papers deal with the classification between COVID-19 and non-COVID-19. And 43 papers actually identify COVID-19 from other pneumonia. And 7% of papers to predict or assess severity. This is more difficult, so we have less papers on this task. And also, in terms for the method, actually deep learning, 80% of papers use deep learning, and 40% of papers using traditional machine learning algorithm. And also, for all this method, 50% of our papers actually achieved over 90% of accuracy, and 40% of the papers achieve 80 to 90% of accuracy. So this is all the papers actually, we summarized by May 31st. So it's like a little bit more than 1 month ago, and all the papers in this area included in this review paper. So now we move to the first questions we want to ask. The question here is, you acquire the images, you want to estimate, you want to classify or want to identify whether this subject has COVID-19 or CAP. CAP stands for the community acquired pneumonia. And this is a work actually United Imaging collaborating with people from Tianjin University, and also from Tongji Hospital in Wuhan, and also Leijing Hospital in Shanghai. So here I just show you, for example, the similarity between the COVID-19 and the CAP from the left to the right. As you can see, more and more infections, similarly to the CAP subject. And we can see more infections for the COVID-19. And also, for example, for the median size of the infection, actually you have the overlap between COVID-19 and the CAP subject. And this is very, very difficult. I will show you more example or statistical information later. So in this slide, I just want to show you, to do this kind of diagnosis, we are going to use the technique I talked in my first part of the this is a work on segmenting infection and also segmenting lung or other structures. Here I select 3 CAP subjects and 3 COVID-19. This is what we call original image. And then we can use our technique to automatically segment infection as lead locations, lead lesions here. And the same technique, we also segment into left lung, right lung for each of these 6 subjects. And also we segment left lung into 2 lobes and the right lung into 3 lobes for all these 6 subjects. And also we segment them, all this left and right lung into 18 segments for all these 6 subjects as shown here. After all these segmentations, we can also see this kind of visualizations for the segment lung as well as the lead infection here. You have less infections for the CAP subject, and you have more and more infections for the COVID-19, as I mentioned before. So just using these techniques, actually we use 189 features, and they have totally 7 different types. Actually 2 types from the radiomic features. In China, people use a lot of radiomic features. So we use two types of radiomic features, and also 5 types from the handcraft features, including histogram, number, intensity, surface, and volume. All these features added together, 189 features. Then we apply our techniques on 2,522 CTs. And for the COVID-19, we include a little bit more than 1,400, and CAP, we have a little bit more for 10 hundreds. So this is the data set for this algorithm recently, for this paper recently accepted by TMI. So this size, I just want to show you how, difficulty for these features or for the classification task. We will show you these 7 original features, visualize them one by one. Let's take a look at first type of features, gray features. You see 2 colors. One is green, another is blue. Actually, you see they are highly overlapped if you use a gray level feature. And also you see the feature distribution actually like a manifold. They are not distributed uniformly in the space. Similarly, for the text feature distribution, in the different pattern, histogram, like all together. And this is the other feature, and we can focus on this surface feature. Surface feature is a feature like a distance between infections to the lung surface. This is very important because a lot of the infections near to the lung, back lung boundary. So this surface actually you see like this kind of manifold, in the space. And all these 7 features, if we use together, then the distribution between the 2 classes actually look like that. It's very, very complex. So this is a way like, our collaborator from Tianjin University, Dr. Changqing Zhang. So he developed an algorithm called the structure latent multiple view representation algorithm. Actually, there are 3 steps in the training. So firstly, we are going to learn completed and structured representation. Here, I just show you each column represents 1 subject. Each row represents 1 features. So we have totally 189 features, as I mentioned you before. So all these samples for each with 189 features will be mapping to the latent representation space using encoding network. People in the sparse learning area, they develop a lot of methods, try to do the latent representation, try to mapping the original features to the latent representation space in order to separate them. Then you can do the good classification. But in the sparse learning method, just like 1-step mapping using sometimes mostly like linear mapping. In this way, actually, the performance is not good. When Changqing was postdoc in my lab, actually, we discuss and we think, this kind of one-state mapping is not good enough. We have to do the mapping, one by one, just like a network, deep learning network. So this is the way also, we use like encoding network. Eventually we use encoding network, and then mapping the original features to the latent space. And then in the sixth step, this kind of mapping, you can do the localizer, then to estimate them. Then in the third step, with all the features in the latent space, you can develop a classification algorithm classified between COVID-19 and CAP. In the testing stages, each subject you have 189 features, then mapping to the latent space, and then classified by the training algorithms you already developed. Then it will output this subject as a COVID-19 or CAP. So this is mainly the technique. And here in this slide, I show you how effective are this algorithm for training and testing. In the training stage, actually, all the samples, training samples, they highly overlap. You see the green samples and the blue samples, they overlap together using our latent learning method. In the learned latent representation space, they are highly separable. And for the testing stage, of course, testing images, they also highly overlap together using same mappings as learned in the training stage. You can separate them very well. So this kind of technique actually can be used as a feature representation or feature mapping algorithm for 5 different methods here, including SVM and neural network. Here you see the yellow. So this is a latent representation. You can see the result from the latent representation is better for using original features for each of these 5 classified for accuracy and also sensitivity and also the specificity. So this technique, file technique, further compared with our method. We have our own classification algorithm. So combined with our latent feature learning algorithm, then basically we can get 90% of accuracy. Actually, it's much better than any of this file method. So I finished talk about force applications. When you acquire the CT image, software can automatically identify whether this subject has COVID-19 or CAP. If this subject has COVID-19, the next AI going to work is whether this COVID-19 is mild or severe. So this is a second algorithm, machine learning based algorithm we have developed. So this is a collaboration with Professor Dong from Beihang University in Beijing. Similarly, we use same techniques for the segmentation, long segmentation, and infection algorithms. And in this way, we get 63 quantitative features. Then we use traditional random forest, but we do have some innovations for our random forest algorithm, particularly for the COVID-19 applications. Just recall, as I mentioned, COVID-19, basically they have a large amount of the infection volume compared to the other pneumonia. And also for the severe case, they have more infection compared to the mild case. So the features related to infection, actually we will select for the top node, including the root node, second layer of the node. In the random forest, usually, for example, even for the root node, you randomly select the features, and then you try to separate into left pass, right pass. You do in this way. Then in the COVID-19 case, because you have the applied knowledge, actually you can incorporate this kind of applied knowledge in the existing algorithm, for example, random forest, and then you can achieve relatively good performance to classify between mild and severity, and then you can get 87% of accuracy. And we found that, GGO volume is the most important quantitative features to estimate severity. I forgot to mention, this is a collaboration with Dr. Jun Liu from Xiangyang Hospital, second Xiangyang Hospital. So after I discuss the technique for the first two applications, then I'm going to talk about third applications. For example, in this case, you found this subject with a mild COVID-19. So then the questions you want to ask is, whether this mild case will convert to severe after some days. And of course, you want to estimate how many days. This like whether this subject will convert to severe or not. This is a prediction or this is a classification problem. And you want to know how many days it will convert from the mild to severe. That means you want to estimate the time. This is a regression problem. So in these applications, actually, we do the joint classification, joint regressions for identify COVID-19 subject who is going to develop to severe from the mild. So this is applications. So here, I just want to show you very interesting, longitudinal image. Of course, interesting for research. Unfortunately, for patients, we have to, say that, and we feel very sorry, for all the patients in the hospital with this kind of disease. This is the images actually we acquired for days 0, like first day when subject coming to the hospital, second day, third day, and day 6, you will see the infection more and more infections. And this is day 7, day 11, day 14, more and more infection. And this is day 7, day 19, and day 27. Infection reduced. You can pay attention to the images. 3 images in the diagonal, day 0, day 11, and day 7. You see large amount of the infections in this 11 days or 12 days. Then in the next 12 days, you see the geometric infection reduced, means absorbed by with the treatment. Okay, so actually this is the images. Just one of the example. Actually, for the severe case, the development of the infections is very, very complex, very complicated, and also very, very nonlinear. Actually, this is the movies I'm going to show you. For the severe case, you will see the infections progress with a larger infection size, and then infection will be absorbed, means the infection will reduce. And you thought, subject is recovering, but suddenly, actually, the infection will enlarge, and you have more, infections, and then going to the next step, absorb, means the infection will be reduced. This is a movie. Actually, I did not show to so many audience before, and this is work actually done by our intern from Shanghai Jiao University and also Hunan University, work with Professor Qian Wang in the Shanghai Jiao University, and also work with Dr. Dinggang Shen in United Imaging. So I'm going to show you the slides. If you are listening carefully right now, I want you to pay attention to this movie. Actually, this movie I showed to the director, Bruce, actually Bruce from Martino Center in MGH. When he saw this movie, he feel, this kind of information, people never saw before, even for the physicians, they did not, see this kind of movie before. This is a movie, population movie. Actually, we align all the, longitudinal images of each subject in the common template space based on the segment left lung and the right lung. Then we mapping the segment infections to the template space. And in this way, you can see from hundreds of the subjects, you see how initially, on early onset, how the infection look like, and then how it look like during the progress, absorption, enlargement, absorption. I will show this movie, pay attention. Information will be shown here. So progress, you have more and more, infections, and it become, severe illness, and then absorb, you have less, infection, then enlarge again, you have more infection, and then absorb. So this is a movie, as I mentioned, built from hundreds of the CT images, longitudinal CT images from the populations, and I can play this movie again, then you can see, how dynamic for this kind of COVID-19 infection development. And it's how difficult to think about initial stage for people, for physicians working in Wuhan. They did not know, how non-linear, how this dynamic, this COVID-19 virus, we develop in this way. Of course, at this time in China, we have, almost deal with all this COVID-19 case, and we have a lot of images over there, and also physicians are relatively have more time, so we can do a lot of this kind of research for knowledge discovery. So let's go to the third applications. As I mentioned, these applications, we have two tasks. First task, actually, you try to identify the case who are going to develop to survey. In this way, if you can do that, you can better manage COVID-19. And also you want to estimate how many times this subject will develop to survey. In this way, you can guide the treatment plan. And also you basically can put the patients in the different kind of, hospitals, for example, for survey case, you can move patient to the special, hospital. Of course, survey case, you always have small number of subjects. In our applications, we have 86 subjects, and you have more mild cases. So in this way, you have to deal with the imbalanced data. And also, as I show you, features are very, very, complex. As I showed you before for the Changjing's paper working with the United Imaging. So this paper actually, was finished by Xiaofeng Zhu from Chengde University, and working with people, actually eight in the hospital from Bing Song, Dr. Bing Song from Huaxi Hospital, and also other people. I will show you more later. Okay. So similarly, for the this algorithm, we still do our segmentation algorithm, as I mentioned in my first talk, first part of the talk. We segment into 5 lobe and 18 segments. So totally plus left, right, lung. So we totally have 26 regions. For each of the regions, actually, we have the 5 HU range using this threshold. And then we can get 390 handicraft features, including volume, density, mass. Then we use a joint classification and regression algorithm, as we mentioned, and these two tasks can share the similar information to improve their individual tasks. And also, we will learn different weights for the different subjects because we have the imbalanced data. Because we are going to use this group sparse learning algorithm, so we can better interpret the results, means where are the features you get and which kind of features. So this algorithm, including regression, classification, and the mapping or weighting functions, they will jointly optimize. Then these two tasks can be, their information can be shared. Of course, there's a lot of constraints for this algorithm. In this slide, I'm going to show you the classification and the regression results. So for a classification, actually, we can get 85% of accuracy, as we can see, as you see here. So the dark red is our algorithm, proposed algorithm. All these 5 methods, as we list here, including SVM, random forest. And also this is RC curve. from our method, the RCQ, the area on RCQ is much larger compared to the FAR method. And this is the results for the regression. Regression means we want to estimate how many days converting from the mile to survey. Actually, for the survey case, we can get correlation coefficients are the 0.5. It's very high correlation coefficients. And even, our difference, our estimated converting day compared to the ground truth is just half a day. And this is actually, the work with Shanghai Public Health, and this is Dr. Fei San, one of our corresponding author for this paper. So I just talk about three, applications using traditional machine learning algorithm, multiple view learning, random forest, and also group sparsity. And in the next, slides, I'm going to talk about the two methods for the first two tasks using deep learning algorithm. So firstly, we want to use a deep learning algorithm to separate between COVID-19 and CAP, community-acquired pneumonia. So in this slide, as I promised you, I will show you more, images, and also most importantly, the statistics for the infections. I show you the two COVID-19 subjects using our technique. As I mentioned, you can segment these infections as a blue region here for COVID-19. Similarly, you can segment infections for the CAP. You can segment all these infections for all the training samples. Actually, in this case, thousands of the training samples, and then you can get this kind of the distribution. For example, the red one here, as you can see, this is for the COVID-19. For the blue one here, this is for the CAP, community-acquired pneumonia. And you see, a lot of, COVID-19 subject has a large, infection size, but, for the CAP, you have small amount of the subjects. On the other hand, for the small size of the infections, you have large amount of the subject, CAP subject, and also the COVID-19, you have small amount of feature. So the most difficult part is the medium size of the infections. You have many, COVID-19 subjects, although you have many actually CAP subjects. This is a difficulty for classifying between the COVID-19 and the CAP subject. So this is a paper actually revised for the IEEE TMI. If you are interested, and you can basically read the paper. Actually, it's already in the account. This is a paper actually, done by the two students from Shanghai Jiaotong University, Xi Ouyang and Mr. Hu. And this is actually, all the 8 director for the radio department in the 8 hospital from Tongji Hospital, Dr. Xia and Fei San from Shanghai Public Health, and also Jun Liu from second Xiangyang Hospital, and Dr. Mo from Jilin, and Dr. Yan from Beijing Hospital, Dr. Ding from Hangzhou First Hospital, and Dr. Qi Yang from Beijing Caoyang Hospital, and Dr. Bing Song from Huaxi Hospital. So a radiologist, director of the radiology department, co-author for this paper. And for this, actually, the deep learning algorithm, I'm going to talk about very briefly, so we pay attention to this deep learning algorithm. And we use a 3D LessNet34, try to get a feature maps, and then do the prediction. For example, classify between COVID-19 and the CAP. So this is the main work. Of course, it's very important, the features we estimate and use to do the prediction for the COVID-19. We hope these features actually taken from the left lung and the right lung, inside the lung, not outside of the lung. So in this way, actually, we generated, and the other view here is we generate attention map. We hope this attention map will be similar to the infections segmented by automatic algorithm I mentioned in my first part of the talk. And we hope this second infection and attention, they can highly match. Means we are going to use MSE loss to measure their difference. Then by use this attention refinement combined with this prediction, we can get very good results. And this slide, I just want to show you the experimental results, as I mentioned before. These are the data like about 5,000 CT images from 8 collaborating hospitals and over 3,600 patients. And we use over 2,000 CT images for training and validation. And we use about 3,000 CTs for testing. For using this about 3,000 test images, we get a result here, various metric as we show here, and we can pay attention for the accuracy. If we use attention guided less IN34, we can improve 2% from this 85.9 to 87.9. So this is using all the images, means you do not care where the infection size is small or large. To see more, clear, more, investigation for our results, we separate in testing data set into 3. One with only 0.5% of infection, and also infections larger than 3%. And this is in between. So you see, we can pay attention again to the accuracy for the small infections. Actually, our attention guide algorithm can improve 3.3% of accuracy. For the medium size, we can increase 2.3%. And for the larger size, our increasement 1%. 3.3, 2.3, 1%. All added together, as I mentioned before, 1%. Okay. So here I just want to show you results. For example, compare the attention map. Here I just show you 3 subjects. Each subject we have 2 view, 1 view, 2 view. Okay, so basically we have 3 subjects. Using our segmentation algorithm, we can segment lungs. This like lung from here. And also we can segment the blue regions here. So this is infections in the original images. As you can see here, all this can be done automatically. If we use I34, this is the attention map. You see features, some features actually get from outside of, this is a lung, from outside lung. If we use attention refinement module to guide IN34, you can get attentions like this. This attention is very similar to the segment infection. You can compare across these 3 maps. Of course, you can compare 3 maps in other subject. You see attention actually outside of the lung, similar like here. Okay. So in my last part of the talk, actually this is a second deep learning algorithm for answer these questions. So this is the questions actually we want to ask is if you have the COVID-19, where the subject is mild or survive. So this is a work with Kelly He from Nanjing University, and also we work with people, particular corresponding Dr. Jun Liu from Second Xiangyang Hospital, and also his student as co-first author here. So all the data I'm going to talk about actually from Dr. Liu. So this is actually, remember, for the first deep learning algorithm, as I mentioned, we use a 3D model. But I will show you in the later slides, the variations for the CT images acquired from the different CT maker, different hospital, different stage of the COVID-19 period are very, very complex. And as I mentioned, in initial stage, when you acquire the CT, because CT is a highly, needed, particularly in the Wuhan area. Then, you cannot, acquire, for example, thin CT, maybe, just a 6 CT, 6 slice CT in many hospitals, and although in many cases, actually, they are missing slice in the 3D CT image. If you use, 3D images, all the 3D image-based algorithm will not work. So in this way, we develop a second deep learning algorithm based on the patches for each slice. For example, patch from this, we put here, patch from this slice, we put here. So you have all these patches. And we do the encoding, and then each of them, they have own the feature. Then we do the embedding level global contrast pooling. And we hope these learned features will be learned for the patches actually related to the survey and the non-survey. Other patches, even you sample from them, you will not learn feature for them because there's no any contribution for you to estimate a survey or non-survey. After you get all these feature vectors for each of these patches, you will do the image level global contrast pooling. Means, you get features for the image level. Then you do the classification as survey or non-survey for the subject. Of course, this is a method. Again, as I mentioned before, we hope all these features used to estimate a survey and a non-survey actually select from the long area, not outside of the lung. So in this case, we add another decoding part, try to segment lobes from the lung. For example, you pay attention to this patch, actually is a patch, original patch here. You can classify, segment them into the lobes, although this patch corresponds to this patch and this two corresponding to this two. So in this way, basically, you also do this kind of labeling, segment lung, also segment lobes, and you hope, the features used to segment lung and lobe also will be used to guide, the classification for survey and non-survey. So in this way, so basically, algorithm performance can be improved, and also you can better interpret your result. And one thing we need to mention here, segmentation is not our goal. Segmentation is used to guide the classification. So you don't need to have very accurate segmentation results for the output of these channels. So by using this method, actually, we first apply to the 666 case from the 7 institutes and totally 242 subjects, 51 subjects actually with survey status. And then for all these 7 institutes, they use 4 different CT makes, including United Imaging CT. And the resolution actually, particularly the number of slides range from 23 to over 300. And more importantly, for spacing, the slide thickness can be about 4 to 10 millimeters. So that means the thickness range a lot. This is also shows the importance of using patches from the 2D slides and then combine them together, particularly like instant, multiple instant learning algorithm, then you can do the classification. So using our algorithm as a result show here for the accuracy, actually, we can get much better performance compared to the best method we compare here. So this slide is actually going to summarize my talk. Actually, I talk about AI applications in the whole pipeline through play imaging. This is I call the play imaging before imaging for contactless imaging using UAI, actually United Imaging Intelligence technique on camera. Actually, this is a technique I forgot to mention. This is a paper already accepted by IEEE translation on the medical imaging. This technique is developed by people in United Imaging US. Actually, this company is in Boston. Also, I talk about, the automatic algorithm for segment infection, segment lung, lobe, and segment in order to do the automatic communications. With all these kind of features, I talk about the three methods using traditional multiple view learning, random forest, sparse learning for diagnosis. And also, we use the deep learning algorithm. We hope, we don't want to use this feature extraction algorithm. Deep learning actually incorporate segmentation, feature extraction, feature selection, classification, everything in the one framework. Then, all the error in each step, they can jointly optimize it. So in this way, the performance, usually I believe deep learning will be better than the traditional algorithm, particularly if the traditional algorithm just separate into different pieces. For example, segmentation is one algorithm, feature extraction is one algorithm, classification is another algorithm. If we incorporate them together, there's no any communications between them, then their performance cannot be optimized. So thank you. This is my talk.